Okay, so I thought I would just do another example of a friction problem. Remember in general that friction is the force that opposes motion. So when you're trying to figure out how to draw your friction vector, you need to figure out which way the object is moving, and then the direction of the force is in the frictional force in the opposite direction. So for number 10, calculate the deceleration of a snowboarder going up a 5-degree slope, assuming the coefficient of friction for waxed wood on wet snow. So we'll have to look that up in the book. Be careful to consider the fact that the snowboarder is going uphill. So if I come over here and draw my snowboarder, I'm going to just draw a little velocity vector here to remind myself this is the direction he's going. So if we draw the forces acting on this person, we have the normal force that's always perpendicular to the surface. We're going to have the weight that always goes straight down to the center of the world. And if he's going up, then the force of friction is going the opposite direction. Yikes, I got all kinds of things going on here. So here's the force of friction using that motion. Okay. Go ahead and write F sub k to show he's moving relative to the snow. So it's on a ramp. So this is one of those types of problems where it's going to be helpful to tilt our axis so that our x-axis is along the snow and our y-axis is perpendicular. If we do that, then we need to go ahead and take our weight vector, an x and a y component. Let's see if I can, this little pen, call this wx, call this wy. Similar triangles, this is your 5 degrees, that's right here as well. So we have our free body diagram. We're going to go ahead and call this the positive direction. Doesn't really matter as long as you are consistent through your problem. So we're going to do the sum of the forces in the x equals max, and the sum of the forces in the y equals may. So in the x direction, it looks like we have wx pointing in the negative direction, and we have friction pointing in the negative direction, and we have equals ma. And this a I'm going to leave as positive because in the moment he's actually moving in the positive direction. We're going to end up getting a negative value because he's decelerating as he goes up the hill. In the y direction, we look at our picture and we have the normal force pointing up, and we have w sub y pointing down, and this is 0. Why is it 0? Well, since I tilted the axis, there's no acceleration in the up off the snow or down through the snow. Therefore, there is no acceleration. So the normal force is equal to w sub y, or the normal force is equal to mg cosine 5. Sorry, my spacing's not very good. Over here, I can write negative mg sine 5, sine because the x component is the opposite leg, minus, instead of the force of friction, I can put mu times the normal force, which in this case is mg cosine 5, equals ma. Notice that the mass of the snowboarder doesn't matter in this problem. So we need to look up this mu value to be able to continue the problem, but we know g is 9.8, the sine of 5 is a number, mu is some known value in a table, g is 9.8 cosine 5, so we have enough information here to actually find the acceleration of the snowboarder up the ramp. Okay, so I just looked that up, and we're going to end up with negative 9.8 sine 5 minus 0.1 is mu times 9.8 cosine 5 equals a, and so a will be equal to a negative, so it's a negative 1.83 meters per second squared. And if they gave me a kinematics problem of some sort, I could actually do kinematics because the connection between the sum of the forces, Newton's laws, and kinematics is acceleration. So if I knew how fast the snowboarder came into the beginning of this slope, I could figure out how far it took him to slide up to a stop or something like that. Okay, hope that helps.